So in our first video on making alcohols, we looked at two different general categories of making alcohols. One is adding a hydride reagent that did nothing to extend the chain but converted a carbonyl compound, an aldehyde or a ketone, into alcohols. And then we had a carbon nucleophile that if we added that, we extended the chain and made a new carbon-carbon bond, converting again a carbonyl compound into an alcohol. So let's take a look at these reagents a little bit more closely. Let's grab another sheet of paper here and talk about the hydride reagent here. And so there are two different types of hydride reagents, and they each produce a hydrogen with 2 electrons on it and a negative charge. And the first one of these is called lithium aluminum hydride. Lithium aluminum hydride. So this reagent has is composed of a lithium ion, positive charge, and then aluminum hydride that has a negative charge. And so aluminum is covalently bonded to 4 hydrogens, and then it has a net negative charge on the aluminum atom there. And so most of the time when we see a hydrogen attached to another atom, we see a hydrogen attached to an more electronegative atom, like oxygen or nitrogen or something like that, or something that is similar in electronegativity. Carbon is actually a little bit more electronegative than hydrogen is as well. But aluminum is a metal, and it turns out that aluminum is more electropositive than hydrogen. And so hydrogen has an electronegativity of 2.1 and aluminum has an electronegativity of 1.5. So in the rare case here, hydrogen is more electronegative than the atom that it's attached to. And so what does that mean? Well, it means that when the bond breaks between aluminum and hydrogen, the electrons would prefer to go to the more electronegative atom, and so when this bond breaks here, then we end up with the aluminum being neutral with 3 hydrogens left, and we have produced hydride. So that is our first hydride reducing agent. Our second hydride reducing agent is sodium borohydride. Oops, boro, that's BORO, hydride. NaBH4. And so you see already a similarity in the name and the structure. Let's draw out sodium borohydride. We have the sodium ion by itself, and then the borohydride, a boron instead of an aluminum, with 4 hydrogens attached to it and a negative charge on the boron. So there is a difference in electronegativity between boron and hydrogen hydrogen is 2.1 electronegativity and boron is 2.0. So not nearly the difference in electronegativity you see up here. It's actually a relatively small difference in electronegativity, which means that it's not going to be as reactive, and this bond isn't going to break as readily, putting the negative charge on the hydrogen. But it will break, and we end up with borane and H-, which is our hydride. And so, what do we see here? We see a hydrogen attached to a less electronegative atom. Then it ends up taking the electrons when that bond breaks and forming hydride. And the lithium aluminum hydride we said was more reactive, and that will become important when we're comparing how it reacts with different electrophiles, and the sodium borohydride is less reactive. And what you will see here is that both of these are strong enough nucleophiles that they will both react as shown here in the skeletal reaction here. So both lithium aluminum hydride and sodium borohydride will produce H minus, and then the H plus is coming from, we're adding H3O. So let's draw out a couple examples here. We're starting out with an aldehyde or a ketone or something like that. Let's make acid aldehyde here. And in this reaction, then, it's a two-step reaction. Number one, you add lithium aluminum hydride or sodium borohydride, either one works. And then step number two, you're adding your acid to add the proton on there, H3O. So we're not going to draw out the mechanism here. We've looked at the basic mechanism, adding H minus and H plus, and these are the reagents that provide the H minus, the hydride, and the H plus. So the net result here is that we have broken the pi bond here, and we've made an alcohol. We had this original hydrogen, and we have added the other hydrogen here. So lithium aluminum hydride is producing this hydrogen, and then H3O is producing this hydrogen there. Okay, so maybe one more example. Let's make a ketone, cyclohexanone here, and we are going to then react that, and let's use the other reagent here, sodium borohydride, followed by H3O, and again, we are breaking the pi bond. We're adding from sodium borohydride, we're adding the H minus here, and that makes this a negative charge, and then that picks up the H plus there, and that's the second hydrogen that has added. So these are the hydride reducing agents, and you can start out with an aldehyde or a ketone, either way, and you can use lithium aluminum hydride to react with an aldehyde, or you can use sodium borohydride to react with the aldehyde, and same with the ketone. Doesn't matter which one you use, and you'll see different examples of them being used. Sodium borohydride is a little bit safer because it doesn't react as quickly and isn't as exothermic, but both of them are good for that. So this is talking about the hydride reducing, or hydride. They are actually reducing agents because they're adding a hydrogen. But this is how we add the hydrogen to make alcohols, and then in the next video we will talk about how to make alcohols by adding the carbon nucleophile, forming a new carbon-carbon bond.